All right, welcome back to 12 Spec. So, what we're going to be doing today is starting the last topic of differential equations. So, this topic will see us through to the end of the term with the test planned for pretty much the last day of term. So, whichever day you are last at school in terms of a maths lesson, whether it's the Monday or the Wednesday, you'll just sit that test on that last day, so probably the Wednesday. So the test is a notes and calculator permitted test, just like most of the others. But let's get straight into it. So effectively, this whole topic is based around the idea of looking at the derivative, but maybe in a bit of a different way compared to what we looked at in methods. So what we're looking at here is effectively using the chain rule or just doing a derivative to an expression rather than an equation. So that doesn't make much sense without seeing an example, but just before we get started, I'm just going to show the chain rule, and that's really what's going to underpin this entire topic, really. So effectively what the chain rule is just saying is if you're trying to differentiate on a function that is not based on the variable that you're trying to differentiate with respect to, so if I have a function f of x and it's actually equal to a function that is based on a variable u, then what I have to do is if I differentiate that f of x function, basically if I try and differentiate it with respect to x, that's what the little dx on the bottom of the fraction represents with our normal derivatives, then when I do a derivative of a function not based on that variable, I must take that into account by effectively timesing by the du by dx. So what that does is that just cancels out the effect of the u variable. So you can think about it in two different ways. So I've got one that's got a function notation version and one that is just the normal definition that's based on the fraction definition, where the du effectively just means the limit as the change in u goes to 0. So effectively why we have to times by that du by dx is to cancel out with the du that would have been generated if we did the differentiation of that function based on u. So if I am able to cancel out those dus, then I effectively have found dy over dx, or just the derivative of y with respect to x. So what does that actually look like when you effectively try and work out something like that? So I've got an example here that is looking at how do we find the derivative or the slope or the gradient going around a circle. Okay, so you might think that's very straightforward, like that's probably just similar to what we've done before. But if you have a look at the circle equation, what we have here is a x squared plus y squared equals 4, where effectively the circle equation is this, the general form of a circle equation, where you can think of it as a term with x subtract a constant and a term of y subtract a constant squared. Those constants give you the center of the circle, so the a and b are just 0, which is why the circle's on the centered around the origin, and the radius is that equal constant squared. So that'll be effectively 2 squared in that position, and that's why we have a radius of 2. So how would you find a statement suggesting what is the gradient around the circle? So like, what is the slope of a tangent that is touching the circle at a particular point? And can we find an equation for that? So using our normal differentiation techniques, you would have to rearrange this function until you get y equals all by itself with everything else on the right-hand side, and then do your normal derivative laws. And those laws still work. We've proven them, they are true, but they just don't quite fit the scenario here. So what we want to do is we effectively want to differentiate this entire expression and equation by dx. So how do we show this? So effectively what this says is I want to do a derivative with respect to x on the entire equation, and I'd just like how you times an entire equation by like 5 or something, you've got to do the derivative on every single component for this statement to still be true. So why do we do this? Well, it's effectively if you have two different variables that are based on different variables. So we have x squared plus y squared. Those are two different variables. So we're going to affect these two statements differently because we are differentiating just with respect to the x variable. So we want to find the change in the x variable over time. That's effectively what we're trying to do. However, we have the trusty chain rule above to help us figure out, well, if we want to find the change in the x variable over time with respect to it, what was if I got something with a y variable? Then all you have to do is use the chain rule. So we end up breaking up this expression into its components. So the normal laws of a derivative stay true, that you can break apart adding and subtracting expressions into their components. This derivative with respect to x, when you're actually doing it on the x squared, that is actually just a normal situation. That just ends up in a 2x. So effectively, all the derivatives we were doing in the past, so we've got our x to the power of 3, whatever, plus 4. When we were doing those normal derivatives, all of those expressions actually had a little imaginary d over dx next to them because we were differentiating with respect to x as we were doing those. Except sometimes when you have expressions where there's different types of variables present, then we just have to show that notation just to tell the reader, well, which derivative are we working on? This goes to 0. So this first term goes to 2x, and then the next term goes to, again, you do the derivative just like before with the chain rule. You do the derivative normally, but then you do have to times by the d variable that you're trying to differentiate with respect to, and then you have to times by the d variable you have divided by the d variable you're trying to differentiate with respect to. So we've got the dy, because that's the one that is different, and then dx is the one I'm trying to differentiate with respect to. And then the d over dx with the constant, the 4 has no variable. In other words, that just goes to 0. So if it's not changing at all, it's not going to change with respect to x. Therefore, it's not changing at all, goes to 0. And then you have a little expression that you can rearrange and then find the gradient all by itself, or the dy over dx. Rearrange, get the negative 2x over there, divide by the 2y. And we get an expression of dy by dx negative x over y. So that would tell you that if you could substitute in the coordinate around the circle, so you need both the x and the y because those are both in the answer. So if I subbed in this case, x equals 0, y equals 2, the answer was negative x over y. We end up with an answer of 0 over 2, or in other words, 0. So that's why that gradient is flat. Let's pick something like over here. So 2, 0. What does that become? Negative 2 over 0. That is undefined. And in terms of a gradient, that means straight up and down. So basically, you cannot divide by 0, and that ends up being a vertical line, undefined. So you, depending on the situation and what you find as the answer, you can find the gradient in a zone, in a specific coordinates, x value. You just got to substitute in and figure out what the answer is. All right, so let's look at some examples. So the first one here, I want to find derivative with respect to x of y to the power of 3. So y is definitely not the variable x, so therefore we do the derivative, but then we need to times by the dy by dx just to cover that. So that's done, not much more you can do there. The next one, dx of 1 over y, that would be the ln y situation, but then you'd have to times by dy over dx. Next one, so this would be a product rule situation, which you can get in these derivatives. So let's do this. So you would do the derivative of the first one, so that x would just be 1, so that'd be y squared, plus the derivative of the other one. So the x is all by itself, like don't do the derivative of it. Then we have 2y and then dy by dx because we did a derivative of the y. So this is just an example of you only do the dy over dx when you've actually differentiated the y squared, or the variable that is not the one you are trying to do the derivative with respect to. So did we get the answers? Yay, we got the answers. Okay, keep going. Okay, next few. All right, so next thing, find dy over dx. Okay, so in these ones, you're not going to get dy over dx straight away, so you need to do the d over dx. So how do you know you're going to generate dy over dx? It's because if you do a derivative with respect to x, that will give you the bottom, and you just need to make sure there's a y in there somewhere, which there is. So if I do this, and then you just got to show it on both sides, that went up with 2x there plus 3y squared dy over dx. They'll go to 0. And then overall this would be 3y squared dy over dx equals negative 2x. And then you rearrange until you get what you want, dy over dx. All right. So if we do another one, so you do the same thing over here, do the derivative, and you know there's some y's in there, so you know you're going to get a dy over dx. All right, so we know that side goes to 0, so that'll go to 1 plus 2xy plus x squared dy over dx. So that was a product rule situation. Then we've got 3y squared dy over dx. So let's get rid of all the y's to the other side and x's, everything that is not dy over dx. So that'd be negative 1, negative 2xy. All right, and then we can take a common factor of dy over dx. So think of dy over dx as it's just a number, nothing that fancy. And then we can chuck that down to the other side. That one's a bit uglier. All right. Find the gradient of this at the point where x equals 2. So gradient meaning dy over dx. So they're assuming we are talking about a y and x Cartesian plane. So again, we need to find the derivative with respect to x of everything. All right, so that would be 2x plus 3y squared dy over dx. Then that would be 0. All right, and then that would be negative 2x over 3y squared, and then we just need to sub in x equals 0. Okay, so you're going to notice that we need a x and a y to find the gradient. So we need to find the actual coordinate in the original statement. So we need to actually find the y value first. So that should be a red flag. There's two unknowns. So we need to sub 2 in there. So that becomes 4 plus y3 equals 5. Y is equal to 1 to the power of 3. So therefore y is equal to 1. Going to assume we're only dealing in the real numbers for this because this would generate imaginary numbers if you allowed it to, which we do not want unless it suggests it wants it. All right, so then we sub in negative 2 times 2 over 3 times 1, and that becomes negative 4 over 3 gradient. So that would be the gradient of a tangent, or at that specific point on this function, whatever that function looks like. It looks a bit mad, but there you go. All right, so that should get you started for 8a. So effectively all we're doing is the application of the chain rule in equations where there are two different types of variables. So the next chapter, 8b, is actually looking at what happens when you have 3 variables in play, or effectively 2 variables that are in the problem, and you introduce the idea of a third variable just to get 2 different gradients or rates of change in the same problem. So one of the classic examples is if you have 2 different variables and then you introduce a third being time. So what happens over time as you change these variables? You would have to be given some information about the time aspect. So maybe it's the speed of the ladder moving. Could be the time. There could be a time function with the y and x variables in it. So what are we looking at here? We're looking at the drop really of a ladder over time as it's pulled out from the wall. And we're looking at the values of the horizontal distance and the vertical distance of the ladder against the wall and horizontal against the floor. So overall, we get a Pythagoras equation, and we can actually use implicit differentiation to obtain a rate equation for this speed of the ladder moving horizontally and vertically. So what you would do is you would obtain an equation using Pythagoras. So that would be Pythagoras on that triangle. And then if you actually differentiate with respect to a third variable t, you can use the same idea that we did in the previous section to come up with a statement. So if we differentiate 2x, but a new variable, so that would be dx over dt. Same thing for the y, dy over dt. And then the other one will go to 0. You can obtain a statement for the rates of change for the x and the y. So you can just leave it like that if you like. And what this relates is the change in x over time, and it relates that with the change in y over time. So let's explore this example further down below. So here's some steps that might be useful. If you like, you can write them down. But basically, the solution is to approaching any problem is draw a diagram if there's a bit of a description about, I guess, an event. If you can draw a diagram, you should. Write down everything that you know about the problem. Try and come up with an equation. So unless you have an equation to differentiate, you cannot do any maths. Maths requires inequalities and equations to actually take away some new information. And then you'll probably end up having to do some implicit differentiation and solve for what they ask for. So that's the general structure of these questions. So if we have a look at this first example, I believe it's similar to the ladder one above. So 5 meter long ladder rests against a vertical wall with its feet horizontal on the ground. The feet on the ground slip, and at the instant when they are 3 meters away from the wall, they are moving at 10 meters per second. So what they're effectively saying is when x equals 3, so 3 meters from the wall, that's horizontal, you are moving at 10 meters per second. So when they say they mean the feet, i.e. the x speed is 10 meters per second. What speed is the other end of the ladder moving at this instant? So they want us to find the vertical change in the vertical speed or rate of change. Okay, so because we did this thing before, so that was y, that was x, that was 5, we did get this expression. Okay, so we can also get the y variable at the point of x equals 3, but we'll do that in a minute. And we also saw that if you did that implicit differentiation, with respect to time, so if we were doing this fresh, how would you know you were doing it against time? Because the variable they talk about in the next section is meters per second, or in other words, they want a distance divided by time, and they're looking at a rate. A velocity is a rate, so i.e. the first derivative. If they're talking about acceleration, that would be the second derivative, which I don't think we'll see too much of in this section. Anyway, so if we do the implicit differentiation, you get this. Okay, so then we need to find dy over dt. So we know what dx over dt is. So that was plus 2 times 3 times 10 equals 0. 2. And then we do need the y as well. And effectively, all I'm doing is filling in all the unknowns. I'm trying to fill them in with all the data that we're provided. So you're going to notice that there was a second piece of data missing, the y answer. And so we're going to need to go back to the original equation to get that y answer. So effectively, I get the idea in my head of I get an equation in the form that I need. I figure out what I know and what I try to find, and what I try to find, and then what I don't know. So the question mark here is like what I'm trying to get. The cross means I need that data and I don't have it. Tick means I've got it. So that just allows you, as we get more and more variables, to keep track of what you're trying to find and how to get it. So I need the y. So I can get the y from here, just another function that's got the y and the rest of the data I know. So this is close as we're probably going to get to like engineering problems where you just get a bunch of different unknowns, you just slot them in wherever they fit, and then you try and get an answer. This is the closest I've felt to doing engineering for a long time. It's probably for the best. And we've got 16, and then you get an answer of plus or minus 4. So then you'll have to chuck in, well, because we've got two different y numbers here, you need to think about, are both of these applicable? So the y value being how far up the wall we are. -4 would suggest we are below the floor. So -4 is not going to work. We only have one answer. Sometimes you will get things that both work. Like if you were like, had either side of like, I don't know, a bridge or something, and you got a plus and a minus x value, you could actually be on either side of the bridge. Like that makes sense. You would have to split your working off into two different sections and then continue on. Like if it was positive, this is the answer. If it was negative, this is the other answer. In this case, we've only got one y value that makes sense, so we sub that in. And dy over dt I want. So then we get a bunch of numbers that we can, I'm just going to chuck that to the other side. So that would be 6 times, so that would be -60. That's a very large negative. And the answer would be this, whatever this is. So if we divide that by 2, we get 30 over 4, 15 over 2. So -7.5 meters per second. So as the x speed is 10 meters per second, the y speed would be a -7.5 meters per second. At the instant you are x equals 3 away from the wall, 3 meters away. So this second example here is going to be one that is dealing with angles. So how do we treat angles in this way of looking at different rates? So I've got a triangle, ABC is right angled, and the right angle is at A. So that would just be B and C, doesn't matter which one's B and C. AB is 20 centimeters, and ABC, so this angle in here, increases at a constant rate of 1 degree per minute. So I'm just going to make that theta. We don't know the angle yet. So the change of 1 degree per minute is basically saying d theta over dt equals 1 degree per minute. So that's effectively what that means. At what rate is BC changing? So BC over here, we'll just call that X for now. At what rate is BC changing when ABC measures 30 degrees? So theta equals 30 degrees. Okay. And we want to know the rate at which that unknown is changing. Whew, it's quite of a situation. So you can see my strategy is draw a diagram, fill in all the information I know. I basically just chuck it all down on a piece of paper. And then we start to try to form equations. And once we've got some equations, we stick the data with the equations and we get the answer. That's the strategy over and over again. Okay, so you can see here. All right, let's come up with an equation. So all we need to do is link the variables together in an equation. So if we have an angle, a side, and another side, we can use trig to come up with adjacent over hypotenuse. So we can use trig to come up with those equations, and then we can do we want the derivative of d theta over dt, so that suggests that we probably need to do dt to both sides, that derivative, 20 over x, and that also confirms that we need dx over dt, so that confirms that we did need to do derivative with respect to t on x as well. So if we do the derivative of cos, that is negative sine theta equals, that would be 20 x to the -2. So that would be -20 then. And there will be I should probably give myself some more space, d theta here and a dx over dt here. Okay. We've got our differential equation to work with. So then we just need to use the rest of the data to help us get the answer. So we need to find an answer for d theta over dt. So we've got that in degrees per minute. Now, I'm just going to put this in giant red. So the derivative units for angles must be radians. Now, why is this the case? It's because when you actually differentiate these trig functions, like if I differentiated cos just then, technically that is the cos of theta plus x, or plus h. Take cos theta over h. Now, when you actually solve that and you get negative sine theta, if you're actually in degrees, then there's a few extra like factors that come out, like some extra timesing that you have to do. And funnily enough, if you actually are in degrees, the timesing factor that you must times by is the factor of getting from degrees to radians, which is pi over 180. So that itself is like you're actually forced to go into radian units when you do this timesing in order for that limit to actually work, for that derivative to actually work. In other words, when you do derivatives, you must be in radians, and even if you don't do it, technically you should actually times by that pi over 180, and it will actually force you to go into radians anyway. And that's just to solve that derivative, okay? So I guess as a piece of an argument, and I actually kind of forgot about this, of why you should use radians for angles rather than just degrees, is because when you deal with their derivatives, you are actually forced to be in radians anyway. When we do our d theta over dt, that must be in radians. So that would be 1 times pi over 180, or in other words, pi over 180 radians. And I'll go back to green now. Sine theta. So the only thing we want to have left is dx over dt. So we need sine theta. We've got an angle to work with, and we need x. Okay, so we need x. So that could come from the original statement. So let's start working on this. So let's work on the, we need theta. So if we, we need x. So if we have cos of 30 equals 20 over x, then we can rearrange that to find x. So again, this one, because we're using degrees for that calculation, it's going to come out as just a number. So the only thing we have to make sure it must 100% be in radians in is actually the derivative. So this thing can actually be left as, this is going to be spat out the calculator like this. So they can just be left in degrees. We get an x value. We needed sine theta. So negative sine theta of negative sine 30 is negative 1/2, I believe. Yep, negative 1/2. Okay, so if we put all this together, we get a negative 1/2 times pi over 180 equals negative 20. So the x here is to the negative 2 power. So we need to do 40 that to the negative 2 power dx over dt. And then we'll just clean up the bits. I would probably recommend only cleaning up one bit at a time. So let's clean up the right-hand side. Let's just see what that looks like. So you just want to avoid oversimplifying or over-rounding if you get decimals, that's all. So if that comes out to be negative 3 over 80, that would be negative pi over 360. And then we can finally rearrange, and that would be negative 80 over 3 times negative pi over 360. So that would be 2 over 27 pi. So this would be the exact answer if they asked it for exact, but if we get that a decimal, that is the change in the size of that length is 0.233. Now go back to the question. It was in centimetres and minutes, so this answer would follow along centimetres per minute. All right, that's it. So good luck with these.